Hi, my name is Kenneth Ramos, and this is my material video project. So what's my favorite type of material and why? The materials that interest me the most based off the guest lectures were between thin films and polymers. However, because I was more familiar with polymers and less familiar with thin films, I was more interested to know about something I didn't know. So in this presentation, I want to give an overview of thin films generally, discussing topics like what are they used for, what are thin films, and then I want to give an overview of thin film synthesis, and then give an example experimental process of the synthesis of thin films. One of my goals is to give a concise but easy to follow presentation so that anyone without prior knowledge to this subject has a general understanding of thin films. So what is a thin film? Thin film is a layer of a material on a substrate with a thickness ranging from fractions of a nanometer to several micrometers. The picture on the bottom left represents a yellow layer thin film on the top of a substrate. The substrate can be glass or a specific material suitable for the desired thin film like alumina or something. Thin films do not just have to be one material, but different materials stacked on top of each other. The image on the bottom right represents stacked thin films of indium, selenium, and copper on top of a glass substrate. The thin layer of a material may introduce new properties not prevalent in its bulky state. Because of this, there may be new interactions between two materials in their thin film state that would not show in their bulky state. Thin films also have a broad range of applications. They can be used as electrical operating coatings. These are thin layers of elements like copper, aluminum, or gold, or silver, having numerous purposes in electrical devices, for example circuit boards. Another application is photovoltaic cells, where thin films have applications in things such as solar cells. There is a vast amount of different types of applications within thin films based on the material and element, and I want to cover later on an experimental process of an element that has applications to electrical and voltaic technologies. So how do we create thin films? Thin films are created with different deposition techniques. These deposition techniques are categorized between a physical deposition or a chemical deposition. The difference is, for a physical deposition, the chemical composition of the material doesn't change. Basically, it's like moving a material from one place to another. However, for chemical deposition, usually a chemical reaction is necessary in order to create the desired thin film. As we can see from this image, there are a huge variety of different techniques, like laser evaporation, chemical baths, or sputtering. However, when creating a thin film, we want to use the simplest technique with the lowest cost that produces the highest quality possible. So I want to go over specifically electron beam deposition in this presentation. Electron beam deposition is a physical deposition technique that involves evaporation. And I want to give an experimental example using this technique. So basically, this technique makes use of an electron beam, which electrons are made to hit the target material, thus transforming the material into a gaseous state and coats itself onto the substrate above. So in the image on the bottom right, we can see an electron beam curving and hitting the material. The material turns into a gaseous state and hits the substrate above. So in the next slides, I want to delve into an experimental process based on an article making molybdenum disulfide thin films. But first I want to discuss on the significance of molybdenum disulfide MOS2 thin films. MOS2 thin film recently this year has been receiving intensive attention due to its potential use in a wide range of applications. In particular, this material has unique uses for catalysis, optoelectronics, solar cells, like mentioned before, electrodes, transistors, and many more. These versatile applications demand large-scale synthesis of MOS2 thin films. So the creation of these MOS2 thin films poses a challenge. High cost and low scalability methods like chemical vapor deposition, molecular beam epitaxy, and sputtering are viable methods for creating MOS2 thin films. However, like we said, when creating a thin film, you want to use the simplest technique with the lowest cost and produces the highest quality possible. So the use of a cheaper and higher scalability technique, such as electron beam deposition, may be a better option compared to chemical vapor deposition or molecular beam epitaxy and whatnot. On the bottom left is an image of molecular beam epitaxy machine, and according to Google, MBE machines cost on the order of $1 million for a system. Now we will go into the experimental process. Stacked elemental layer deposition, cell for short, of thin films of MOS2 were attempted on glass substrate by electron beam evaporation of elemental molybdenum and sulfur. Cell is the process of evaporating the elements independently, forming stacks alternating each other, rather than simultaneous evaporation. This process is considered due to the high difference of melting points of MO and S, which makes simultaneous evaporation near impossible. Before the process was begun, the substrate was cleaned with an HCl soap solution, a meter per second high vacuum with a 3 kilowatt beam evaporator was used to evaporate the materials. Again, cell will be carried out. The molybdenum and S layers were deposited for 30 seconds and 60 seconds respectively to control the thickness of a 1:1 thickness ratio. This was due to the sulfur evaporating to the point of deficiency, so this ratio was done to maintain stoichiometry. The deposited thin films were then annealed. In other words, they were heated in an argon atmosphere at 500 degrees Celsius for 10 minutes, and then slowly cooled. The results are as follows. On the left image, we have a low magnification micrograph of the deposited thin films of molybdenum disulfide before the annealing process, and another graph inside of that image showing its particle size distribution. You can see in the particle size distribution graph that the particles maintained a particle size between 5 to 10 nanometers. On the right is a high magnification of the MOS2 thin films and an EDS spectra. This data was used to further analyze the thin films in a different way, which I will not be getting into for this presentation. I'm just presenting a brief representation of what an experimental process of a thin film would be. Here's another set of images and data. On the left, we have a low magnification micrograph of the annealed thin films and its particle size distribution. And on the right is the high magnification of the annealed thin films and an EDS spectra. And lastly here is a comparative result of a bare glass substrate and a representative MOS2 thin film. Like I said, this data was used to further analyze and measure thin films in many different ways, which I will not be going into for this presentation. These are my references, and this is the end of my presentation. Hopefully I achieved my goal of giving a general, concise and easy to follow presentation on thin films. There are plenty more things to know about thin films, and this was just a brief introduction of some sort.